Today I'd like to do some demonstrations of problem solution using Newton's second law applied to situations that are specifically uniform circular motion. And at the very beginning of our investigation here, I did a demonstration where I put an object on a platform that had strings attached to it, and I whirled it around in a vertical circle. We discovered that even if the object is a beaker full of water, that the water stays in the beaker and the beaker stays in the platform and the whole thing goes around in circular motion. Now that circular motion is not uniform circular motion, because if we were to investigate it, we would discover that as it rises on one side of the motion, it slows down, and as it falls on the other side of the motion, it speeds up. But let's imagine that I'm able to whirl my hand around in such a way that I can maintain pretty much uniform circular motion as I go around. Right, so I'm saying it's approximately uniform circular motion. And yet that beaker stays in place and the water stays in the beaker and the whole thing goes over the top as long as I go fast enough. If I whirl it in a vertical circle and I go slower and slower and slower, at some point the beaker is going to fall off and the water is going to fall out and the whole mess comes crashing to the floor. In order to understand that motion, I'm going to apply Newton's second law to that situation. Here I have a circle in principle of a known radius, r. And I'm going to imagine that it's this circle that the platform travels around with the beaker on it. So I'm going to draw it in 3 different locations. Of course, as the beaker and the platform go around in circular motion at any instant in time, it could be in any position anywhere around the circle. But I'm going to draw it here at the bottom. So I'll draw a little platform here and a little box on there that represents the beaker. That's the beaker in the lower position on the platform. I'm not going to draw the strings because the strings will confuse the diagram. And I'll also draw the same thing. So I'm going to have to draw this and make it look kind of symmetric. Hopefully my drawing skills are with me today. I think that's certainly adequate. Here's the platform with the and then I step back from it and I don't think it's adequate. Here's the platform again, but it's now in, I guess, what we might call the 3 o'clock position. It's on its way up, heading towards the top of the motion. I'm interested in drawing it at the top of the motion as well. And the reason why I choose to investigate this problem by drawing it in 3 different locations is that in each one of these 3 different configurations, the free body diagram is different. If the free body diagram is different, then Newton's second law is applied differently. And I'm going to get different results. Now, I'm simplifying things because, of course, I could draw it in positions everywhere in between. I could, for example, draw it at a position where it's 45 degrees up from the bottom. I could draw it where it's 45 degrees up from the 3 o'clock position, in which case those free body diagrams would be fancy indeed, and I would have to take components and some trigonometry involved and whatnot. I'm not going to do that. I'm going to keep it simple because, in particular, I'm most interested in the behavior of the thing when it's at the top of the motion. Because that's where it gets interesting, because that's where, if I go slow enough, it could fall off. And that's interesting behavior that I'd like to investigate. So what I'm going to do is draw free body diagrams for each one of these locations. When I draw free body diagrams, I typically draw them off to the side. But here, just because it's instructive, I'm going to draw it on the diagram itself. I don't think it'll be that messy. In fact, I know that it won't. So here I am at the 6 o'clock position, at the bottom of the circle, and I look at this object and I realize that it has weight. It has a weight mg directed downward, and it has a normal force n directed upward. You may say, well, wait a second, the platform is connected to some strings and you hold the strings in your hand and whirl it around. Recall the elevator problem. I had Slim standing on an elevator on a bathroom scale and there's a cable on the elevator that pulls upward, but that force does not act directly on Slim riding on the elevator. And so I don't include it on the free body diagram. What exerts a force on the beaker? The platform, and that's a force of contact. What a very boring free body diagram when you look at it because you say, oh, I know what happens here. I know how it goes. The weight is downward, the normal force is upward. I'm going to write Newton's second law, and I'm going to discover that the normal force is equal to the weight. No, because this thing's going around in circular motion. The acceleration is not 0. The normal force is not equal to the weight. In fact, in just a moment, we're going to realize by an application of Newton's second law that the normal force is in fact greater than the weight. So if there was a bathroom scale in this situation, if I did the same thing, but I put Slim on the whirly-gig platform and whirled it all over the place, probably terrifying for him. In the 6 o'clock position, when he looked down at the scale, he would read not his weight, but the normal force, his apparent weight. at the bottom, which we're going to discover in a moment would be greater. But let me finish my free body diagrams first. Now, from the 6 o'clock position, the platform and the beaker, they swing up to the 3 o'clock position. Now, at the 3 o'clock position, the free body diagram is different because the weight, which has not changed, is now downward. Same as it was before. Same magnitude of weight pointing in the same direction because gravity is always downward, radially towards the center of the Earth. But the normal force now points this way. So you see that the orientation of the forces in my free body diagram has changed. The normal force is the force of contact. But the word normal means perpendicular. And so that normal force is perpendicular to the platform. When it gets to the top in the 12 o'clock position, the free body diagram is changed once again because the weight is directed downward and the normal force is also directed downward. So in these 3 different locations that I've chosen to investigate in this particular solution, I have 3 different free body diagrams, which means I'm going to apply Newton's second law in 3 different ways. When it comes to circular motion, the coordinate system that I choose is kind of a funny one. Very often I solve problems with the x and y coordinates. But then when I did the inclined plane problem, I decided to turn the coordinates so that it was parallel and perpendicular. Well, when I'm solving a circular motion problem, I'm looking at radial and tangential. I think we remember from math classes that tangential means a line that passes through the circle at only one point is tangent at that point. That is perpendicular to the radius. So when I look at the forces on my free body diagram, I'm asking myself what forces are radial and what forces are tangential. In terms of circular motion, it is the radial forces that I am interested in because I'll begin down here at the 6 o'clock position and write Newton's second law prepared for circular motion. That is, the sum of the forces that act in the radial direction is equal to the mass times the speed squared divided by the radius. Charlie, I thought it was mass times, I thought the force was mass times acceleration. It is mass times acceleration. But in the case of uniform circular motion, the acceleration is the speed squared divided by the radius. So I have to look at my free body diagram here and write the sum of the forces that act radially. Well, when I look at the free body diagram, I see that the normal force points towards the center of the circle. That is a radial force. The weight force points away from the center. In that sense, the normal force is centripetal and the weight force is centrifugal. The important thing here is that when I apply Newton's second law to circular motion problems, I choose toward the center to be the positive direction. Earlier, when we did problems involving gravity and free fall, I said that I always chose upward to be the positive direction. That was just my choice for problem solving. Choose any way that you like. That's not the case here. I don't get to choose. Toward the center of the circle is the positive direction, which means when I apply Newton's second law here, the normal force is a positive force and the weight force is a negative force. You might look at it and say, well, Charlie, I was going to say that anyway. The normal force points upward and the weight points downward, so I would have said that anyway. Yeah, but bear this in mind when we do the other free body diagram, because it's important, it's going to be essential to me getting the correct answer. So when I write the sum of the forces, it's going to be the normal force, which is a positive centripetal force, plus the weight, which is a negative centripetal force. And so I write the normal force minus mg is equal to mv squared over r. And immediately I get a verification of what I suspected, and that is that the apparent force, or the apparent weight, as we came to call it in the elevator problem, is actually mv squared over r plus mg. So the apparent weight at the bottom is greater than the weight, because at the bottom, the platform has to do 2 things. It has to provide for the circular motion, and it has to support the weight of the object. And so at the bottom, the normal force is greater. Now that I've done that application, the other 2 I can do a bit more quickly. Looking at the 3 o'clock position, the sum of all of the forces that act in the radial direction is equal to the mass, the speed squared divided by the radius. Now look, because of the change in the configuration of the system in space, the weight force mg is no longer radial. It doesn't point toward the center, it doesn't point away from the center, it is tangential. And so therefore, it causes no radial acceleration. It does, however, cause tangential acceleration. That force of the weight is the reason why, as I swing the platform upward, it slows on its way up. Tangential acceleration. I'm not interested in that in this discussion. I'm only interested in radial. And the normal force is the only radial force that I have. So the sum of all of the forces acting radially is simply the normal force. So in this configuration, if I had Slim standing on the platform on a bathroom scale, the reading on the scale would have nothing at all to do with his weight. The reading on the scale would bear no resemblance or relationship to the force of gravity at all. The scale would read mv squared over r. The scale would read the centripetal force only. And since I'm going around at constant speed, in principle, I have the same speed at the bottom as I have at the 3 o'clock position, and then that force would be less. As Slim starts his trip to the top of the motion, he's like riding on the thing on a bathroom scale, he starts to feel light as he goes up. Now in the top position, the free body diagram is changed once again, so the normal force is directed downward and the weight force is directed downward. But now they both point toward the center. And since I insist that toward the center be the positive direction, since I insist that towards the center be the positive direction, these are both positive forces. Yeah, I know they point downward, but I have to think deeper than that. The question is, do they point towards the center of circular motion? Indeed they do. So at the top of the motion, when I write the sum of all the forces that act towards the center, or act radially, is equal to the mass times the speed squared divided by the radius. It is the normal force plus the weight. So if I were to solve for the normal force in this case, the normal force is equal to mg, If I'm solving for the normal force in this case, it's going to be mv squared over r minus mg. So the faster we go, the larger the normal force is going to be. But here's the strange thing, the fun part of it. This gets me an answer that I would not otherwise have had. Now that I've done my Newton's second law, I can ask the question, what happens when I go slower and slower and slower and slower? I know from actually doing the experiment that the slower that I go, the slower I go, the closer I get to this dangerous moment when the whole thing falls. And this Newton's second law equation explains that for me. So I'll just write it like this, that the normal force plus mg is equal to m, the speed squared, divided by the radius. That's my Newton's second law analysis for the motion at the top, at the very top. The normal force is the force of contact. And as I go slower and slower and slower, the normal force becomes lesser and lesser and lesser, until eventually I lose contact, right? If the normal force is the force of contact, then when I lose contact, the normal force becomes equal to zero. That's what losing contact means. So I'm going to force this equation. I'm going to force it to give me the answer that I seek. That is, when does it lose contact? The weight here is being subtracted. So when I calculate mv squared over r minus mg, as long as it's larger, as long as mv squared over r is larger than mg, the normal force is there. But as I go slower and slower and slower and slower and slower, eventually I get to a point where mv squared over r is equal to mg, and then I'm in trouble. And that's exactly what my equation says here. That mg is equal to mv squared over r. When that happens, that's when the fun begins. Notice that I have an m on both sides of the equation. They cancel. The m's cancel. And so g, the acceleration due to gravity, which is a constant of this motion, is v squared divided by r. So the critical speed, if I just do a little bit of algebra, solve, multiply both sides by g, and take the square root, I get a fun answer that I would not have guessed. I get it by careful analysis using Newton's second law. That the critical speed for executing the vertical loop and not falling is equal to the square root of g times r. If you go at that speed, then just when you reach the top, the normal force will become zero. Well, that would be a great deal of fun for Slim, wouldn't it? If Slim's riding on the platform, or you riding in the roller coaster when it inverts, and you're sitting in your seat. You know, the roller coasters, they're designed this way. It's really great when a roller coaster goes super fast, because everybody enjoys going super fast. But a roller coaster is scariest when you go through the top of the loop slowly, because that's when you start to feel the apparent weight vanish. Your weight is mg the entire time. It's your apparent weight, the normal force that vanishes. And that gives your brain the scary feeling like I'm going to fall out of this thing. Now, I could design a roller coaster. Nobody would ever let me sell tickets and invite people to ride on it. But I could invent a roller coaster with no harnesses at all, no buckles or safety gear at all, just a seat that goes through a loop. And if I designed it in such a way that the speed of the roller coaster going through the top of the loop was always just a little bit greater than the square root of g times r, then no one would ever fall out of the roller coaster. But going through the top of that loop would be terrifying, because as you went through it, you would feel like, I'm about to lose contact with my seat. Maybe I'll even make it a little bit less than the square root of g times r, so you do actually leave your seat. That'd be fun. Of course, no one will let me build the thing, because what if it accidentally goes wrong? What if there's a bit of extra friction? What if, I don't know, it hits a goose? No, it actually happened one time. There was a model by the name of Fabio. You can look this up on the internet, it's true. And he was riding on a roller coaster. He got hit in the face by a goose on a roller coaster. It's stunning. What was I talking about? But no, instead, when you get on the roller coaster, of course, there's the big harness that comes down over your shoulders. That's in case the thing doesn't work properly, you can fall out of it. But also, if there's a shoulder harness in the thing, I can let it go through the vertical loop way below that. So you start to fall out and you go up against the shoulder harness. You're like, I'm being held into this thing. To increase the terror in general of the roller coaster. So I understand this in the context of a Newton's second law analysis of the dynamics. So I've got 3 free body diagrams out of this one problem. Now, I can make it more interesting and solve free body diagrams at various locations along the way, that's true. But if I did that, there's going to be components of the weight involved and so forth. It gets a bit more sophisticated. In our course, we're not going to expect you to solve that problem, but you might consider taking down a piece of paper and looking at it and figuring out what the components would be and realize that that problem is completely solvable. Now, there's another problem that I would like to investigate, another example of apparent weight or apparent forces. And it's one that you've encountered in your everyday life. Here I have a circle, but the circle is just standing in for the actual motion that I want to describe, and that is a car going over a hill. So what I'm going to do with this circle of a particular radius r that I know, and I draw, is I'm going to draw in a roadway that goes over the top of the circle. You'd probably realize, driving around the neighborhood in your everyday life, that hills are not circular. But when I'm going over the top of a hill here in my car, so I draw the car in at the top of the hill. So here's the car going over the top of the hill. When I'm driving along in my car, at every instant on the roadway, I can draw a circle in there that is the circular motion that's going on in that moment. So even though the hill is not circular, at the very top of the hill, it's approximately circular motion as I go over the top of the hill. Now, you know what this experience is. If you go slowly over the top of a hill, it just feels like normal sitting in a chair. But if you go fast over the top of a hill, a bit of lightness. If you go really fast over the top of a hill, whoa! As you go over the top of the hill, your stomach floats, you realize something's going on. If you go really fast over the top of the hill, airborne, becomes projectile motion. Yeah, good times. So I'd like to analyze it with Newton's second law to see if I can find the speed that I have to be going over the top of the hill in order to get airborne. Be pretty great. So, does the car have weight? Absolutely. And by the way, the free body diagram that I'm drawing here for the car applies to the passengers as well. So I suppose I could have Slim in the car sitting on a bathroom scale and reading what the normal force, his apparent weight, reads as he does it. So the weight force directed downward, the normal force N directed upward, and now I'll apply Newton's second law. But Sandy, we already did this. You're doing the same thing you did over here. For here, you got the normal force up and the weight downward. Yeah, no, it's not the same, is it? Because toward the center of circular motion is positive. Here, it is the weight force that points towards the center. It is the weight force that is positive, and the normal force is negative. And of course, that makes a difference when I apply Newton's second law. The sum of all of the forces that act in the radial direction is equal to the mass times the speed squared divided by the radius of the circle. So in this case, applying that, what do I get? I get the weight mg as a positive centripetal force directed towards the center of circular motion minus the normal force is equal to m speed squared divided by radius. That is the equation of motion that describes going up over the hill. Notice that if I solve this equation for the normal force, then the normal force is equal to the weight minus mv squared over r. So if car sitting still on the top of the hill, the apparent weight is your weight. The faster you go over the hill, the smaller your apparent weight gets until, now the analysis. mg minus the normal force is equal to mv squared over r. Going over the hill faster and faster and faster until the normal force becomes zero. I lose contact. It becomes a projectile motion problem. Well, look, there's a mass on either side of the equation. They cancel now. And so g is equal to the speed squared divided by the radius. Oh, look, the critical speed for going over a hill, not getting airborne, is the same as the critical speed for going through the top of a loop on the inside. That's just a coincidence in the simplicity of the algebra. That's just a coincidence, simplicity of the algebra, that it worked out that way. But that critical speed seems to be the same. And time and again, we're going to see answers to our questions for the speed that have this sort of functional form with just little modifications to them. And that's just an artifact of the fact that the problems that we're solving are relatively simple, and that the sum of the forces acting radially is always equal to the mass, the speed squared divided by the radius. And so now I have a new set of problems that I can go forward and solve. There are other types of circular motion problems that have these same free body diagrams and therefore have similar solutions. So by examining these problems, I've not only learned how to solve these specific instances, but also an entire family of problems that just happen to have the same free body diagram.